All right, good morning, everyone. I guess it's time to start. Um, Welcome to Math 214. I guess I'll go ahead and say first thing off the bat, I'm not totally sure how I'm going to structure this course yet. This is the first time I've taught it, and I just got the materials from people who have taught it in the past yesterday afternoon. So it's still kind of all coming together. But I will say, as a first rule, I will require that anybody's who is here for the Zoom meeting have their cameras on. Um, it's a little weird being able to see myself and not being able to see anybody else. Up to this point, I've managed to get away with not having to teach any classes entirely online. So I haven't had to deal with this much so far. Okay. There's still 4 people with no camera. Um, I'll give it maybe a minute. If you don't have your camera on, I'm gonna assume you're not actually here, and I'm gonna boot you from the Zoom meeting. Okay. So, hello, how's everybody doing? Thumbs up. God, I hate Zoom so much. This is so weird. Okay. Uh, well, so where should I begin? I guess I'll tell you a little bit about who I am. I know it says Richard down here on the thing. I go by Drew. My middle name is Andrew, so I go by Drew. This is the point when I would normally tell people, don't call me Professor Duncan or Dr. Duncan, because I'm neither of those, but I actually just recently accepted a professorship, and I'll be finishing my PhD Monday of next week. So you can call me Professor Duncan if you want, but you'll have to wait a week if you want to call me Dr. Duncan. I've got a chat here. Hang on. I have to get a camera. All right, be sure and do that. Okay. So let's see. I've never taught Calc 4 before. So I'm sort of relying a lot on the material from the people who have taught it in the past. So I'll try to follow their schedule pretty closely, but it's a summer course. We'll get through what we get through. So we'll see how it goes. Let's see what else. Let me go ahead and bring up the Canvas page. Oh yeah, this is the last class I'll be teaching at UK. So yeah, we might go at a little more leisurely pace than we normally would. Okay, let's see what we have on the. Yeah, like I said, the syllabus is still a work in progress because I didn't get a copy of a previous syllabus until yesterday afternoon. All I know for sure is the time the class meets, which is right now. So you already know that. I'm going to record our Zoom meetings and put them on the class website so that if you're not able to come to class, you can view them on there. Let's see what else. Yeah, I haven't decided on when I should hold office hours yet. I guess if there are times that work really well for you, just send me an email and let me know, and I'll try to tailor my office hour times around what works best for you guys. Okay, let's see. There's normally like the first day thing where we go around and everybody talks about themselves and says their names and what their majors is and everything. I think that's kind of silly, so we're not going to do that. And I can see your names. The only thing is, if I call on you and I mispronounce your name, or there's something else that you would rather be called, just let me know. So I can fix that. Okay, let's see, what else do we have here? I guess you've seen on the Canvas page, we're going to use these course notes. These were written up by Dr. Oceanine maybe last year, I think. So that's under the Files tab on Canvas. I'll probably go more from this online book, the by Jiri Lebel, DiffEQs, Differential Equations for Engineers. That's probably what we'll go by because it's free. Let's see, homework will be through WebWork. We will have tests. You see, I just copied this from what I got from last summer, so I may change this, but it looks okay. We'll have tests every couple weeks on Canvas. Some multiple choice questions, some free response questions. The timing and when we'll do these, I guess that'll be to be announced. Let's see, grading. Web work, 20% final grade. And I guess the rest is exams. Yeah, there's got a lot that I need to change in this. Okay, let's see this. It says students with disabilities. Basically, if you have anything that impedes your ability to do the course that's in any way medically related, go talk to the DRC. They're extremely helpful and they are 100% on your side and there to help you. So I highly encourage you to take advantage of that. Academic integrity and cheating. Don't cheat. Okay. What else do we need to talk about? WebWork's not set up yet. I'll get that set up. I know for sure that there will not be an attendance grade. There are a number of students who are taking the class asynchronously. I guess that's the term we're using for it. And so I'm not going to be taking attendance. If you want to come to the lecture, this is a good opportunity for you to ask questions or to get practice working problems or, just get some clarity on anything that you're not clear on. But it's not required to come. And it'll be recorded, so hopefully the people who aren't able to come, they won't totally miss out on the opportunity to have some immediate feedback. I've only taken up 9 minutes so far, God. So let's see, what else can we talk about? Let me just stop for a second. Does anybody have any questions so far?
When do you plan to do office hours? Has that been decided?
No, it hasn't. So like I said, I'm going to wait and let everybody have an opportunity to email me and let me know what times work really well for them. And I'll try to get it to be a time that works well for the most number of people. So to answer your question, I don't know yet.
I had a quick question about the homework. I tried to look at the WebWork website and it says like all of them are closed. Do you know when like the first one would be due?
No, not yet. So I just got the email back about WebWork being set up yesterday. So I haven't added it to Canvas yet, and so I haven't decided on when I'm going to start putting the WebWorks up. But it will be they'll kind of be in line with as we cover topics. So it will depend on what we get through and how quickly we get through it.
Perfect, thank you.
Yeah, no
On
problem.
the syllabus, it says that we meet every Tuesday. Is that only Tuesdays, or do we meet other days of the week?
Yeah. Okay. So that's the syllabus from last year. I mean, I just copied it. So My plan is to have this Zoom meeting every day. We'll just kind of, I'll work through the material. I have a tablet that I can write on. I left it at home, so unfortunately we won't be doing that today. But my plan is to do the Zoom meeting every day. But like I said, it's, you know, I'm not taking attendance, so,
Okay, thank you.
yep. Okay, anything else before we move on? And again, just a reminder, I do require that if you're going to be in the Zoom meeting, to have cameras on. I know one person told me that they don't have a camera yet, but we have 2 other people. Okay, yeah, how do I fill the time here? So I guess we can start looking at, well, let's bring up the course notes from Dr. Oceanine. So he has put together a PDF, and I think it's pretty good. So let me see if I can get this on a screen by itself. You'll have to bear with me. I have very little experience with Zoom, so okay. See, download, open, and let's do a share screen, and we'll just talk about this stuff. Okay, and I have to expand this so that I can see everybody. Can I do that? Well, I can only see 4 of you at a time, so if you have a question, you're gonna have to yell at me. Okay. So let's see. So where do we begin? Okay, so we have first definitions here. As he starts off right off the bat with talking about ordinary differential equations and first order differential equations. Maybe it's good to do a little bit of an introduction about what exactly the central idea of this course is. So far you've been through the 3 calculus courses, and this has been a sequence of courses where the main thing that you deal with, the sort of thing, the mathematical object that you're working on, is numbers. So if you have like an equation where you have maybe 2 functions are equal to each other, oftentimes we were dealing with functions that were polynomials, and we might want to know the solution to a polynomial equation, maybe some polynomial equal to 0 or something like that. So we would have this expression that is of some variables. They're raised to some power, they're multiplied by some coefficient and all added together. And this would give us a polynomial. And so that variable is meant to represent a number, right? That sort of situation, that's the kind of situation that we take for differential equations, but instead of dealing with variables that represent numbers, now we're looking for variables in an equation that represent functions. So when we solve an equation, a differential equation, we're not looking for a solution that's a number, we're looking for a solution that's a particular function. So it's a function that satisfies the equation. And continuing this analogy, instead of raising a variable to a certain power, what we'll do is we'll be applying a derivative to that variable a certain number of times. So if maybe we look through these notes and see, okay, maybe this is not a good thing in the notes, but I know in the book here, There's some good examples of this. Classification of differential equations. Okay. Here we go, something like this. So you see this form here that looks very close to something that's like a polynomial equation. We have this y that's our variable, and the various terms are, the degrees of the terms aren't exponents on the variable y, they're the number of times we apply this derivative operator. Okay, so we have that in each term. Each term has a sort of order that we are doing the differentiation, and each term has a coefficient. And because in this analogy, we're not thinking of the variable as representing a number, but as representing a function, then our coefficients are now functions of our dependent variable. So y represents a function of x, and x is our independent variable. And so our coefficients can be functions of this variable. Okay, so that's the kind of putting this into context with the other kind of math that you've seen before. So we're solving equations, but the equations are no longer in terms of numbers. Now they're in terms of functions and derivatives, which you're very familiar with at this point. Now the biggest split in differential equations is between if we're talking about functions that only take a single variable. So in this case, we're looking at functions just of this variable x. But we could also possibly look at functions of multiple variables. So let's see if we have an example of that here in the book. Yeah, okay. So here, you'll definitely remember from Calc 3 the idea of a partial derivative. So if we have a function of more than one variable, we can take the derivative with respect to any of the variables of the function. I apologize for the noise here. And so in this case, what we're seeing is this is the second partial derivative of y with respect to t. And this is the fourth partial derivative of y with respect to x. And so there's the possibility that the functions that we're looking for are a function of a single variable or functions of multiple variables. So if we're looking at differential equations that regard a function with a single variable, then these are called ordinary differential equations, or ODEs. And that's going to be almost entirely, or possibly entirely, what we're going to talk about in this class. So just ODEs. But we also have these types of differential equations where the function that we're looking at has more than one variable and the derivatives are partial derivatives. And so those are called PDEs, or partial differential equations. Okay. Here's another example. These are Maxwell's equations of electricity and magnetism. And you'll recognize that the div and curl operators here. So here we're regarding each of these things, D, E, B, and H, and J here, as functions of, they say functions here of X, Y, and Z, but we also have a derivative with respect to T here. So I suppose these should be functions of 4 variables, 3 spatial variables and 1 time variable. Here's some more examples of important ordinary differential equations and partial differential equations. So that's the first big split in the area of differential equations. And for this class, like I said, we're only going to be dealing with ordinary differential equations. So among ordinary differential equations, how can we split things up? This is just the beginning of talking about differential equations. So really the first thing you do in a subject is kind of name everything. So we're just going to be naming things. They're in the solutions of differential equations in practice. Yeah, maybe we'll come back and talk about that stuff in a second. Let's go back one more section. No? Maybe go forward a couple sections. Okay, so let's see, homogeneous and non-homogeneous. I think that's not what I want to talk about first. I want to talk about the order of the equation. So where do they talk about that? Here we go. So this is another way that we categorize differential equations. The order is the largest derivative that appears. So if you remember back to polynomials, we had this concept of the degree of a polynomial, and the degree represented the largest exponent that appeared on any of the variables. So if we had x cubed minus 1, that would be a degree 3 polynomial. There's a similar concept in differential equations, or ODEs. So the order will represent the largest derivative that appears in the equation. So for example, well, we're looking at a PDE here. Let's just look at ODEs. So this is the highest derivative the highest order derivative here that we see here is first order, and first order here. So these are first order differential equations. But here we see the second derivative with respect to t. And so this is a second order equation. Okay, so that's an important nomenclature for differential equations. The next one that we can talk about is linear versus nonlinear. And well, first of all, just the definition. So if we can write it in terms like this, so we can, let's see, if the dependent variable or variables, so this is the variable that represents the function we're trying to find. And their derivatives appear linearly, that is only as first powers, they're not multiplied together. Okay, yeah, so that's basically, if we can write our differential equation like this. So we can take all of the things that are multiplied by y and collect them together to make this y term here. So collecting all of the things that are multiplied just by y, we get something that's just in terms of x, right? So that's this, this function right here. If we take all of the things that are multiplied by the derivative of y and we collect them together, we get a coefficient that's just in terms of x right here. And it doesn't have anything in terms of y, right? So this is not multiplied by anything in terms of y. It's not multiplied by anything in terms of the derivative of y. If we go on to the second order term, if we have one, then all of the things that are multiplied by the second derivative of y, if we collect all those together, it's all in terms of x. So we don't have the second derivative of y multiplied by itself. We don't have the second derivative of y multiplied by the first derivative, and we don't have it multiplied by y. So that basically means that we can take anything that is a linear ordinary differential equation and write it in this form right here. And then we can think of this, if we were thinking of this as a polynomial, then this would be our constant term. So this is things that are not multiplied by any derivative of y. So if we think of this as being the 0th derivative of y, for example. So anything that can't be written like this is nonlinear, and it would be nice if they gave us an example of that. Let's go back to the examples at the beginning and see if there are any. Okay, first of all, you'll see here we have the second derivative of x, the first derivative of x, and then x. And then the things that are multiplied by them, in the case of this M, C, and K are all, they're all just numbers. And so they're not anything in terms of T. So this is a linear differential equation. They should definitely give us an example. Here's an example of a nonlinear equation. So unfortunately, this is a PDE. This is not an ordinary differential equation, but you'll see here this term, the derivative of y with respect to x, and it's multiplied by y. So this makes it a nonlinear equation because we have our first derivative right here and our 0th derivative being multiplied by each other. So we can't take this thing and split it apart and rewrite it in this form right here. We can't write it just in terms of y multiplied by something completely in terms of x, and the derivative of y multiplied by something written completely in terms of x. So this is nonlinear. And this is actually a really important distinction because it will turn out that linear differential equations will be much easier to, it'll be much easier to talk about the solutions to these than it will be to talk about the solutions to nonlinear equations. So this is an important distinction. Okay, so if we have a linear differential equation, we can write it in this form. We call these things the coefficients of the linear equation. And like I said before, these coefficients will be functions of the independent variable. These functions are, yeah, like it says here, they can be completely arbitrary. So you see here the coefficients, well, on this side, the sort of constant coefficient is 1 over x. This is just any function in terms of x. We have an x squared here for this coefficient. We have a sine of x for this one, and e to the x for this one. These coefficients can be completely arbitrary functions of x, so long as they don't contain anything in terms of y or its derivatives. Okay. Here, this is a good example of the distinction between what we're using as the independent variable and what we're using as the dependent variable. So in this example, we're looking at the dependent variable being x, and we're, I'm sorry, it's really noisy here. I apologize again. My office is in a really noisy neighborhood. So we have on this side the thing that's in terms of the first derivative of x, and then over here we have the term that's in terms of just the independent or the dependent variable itself, x, and we see that it appears as x squared. So we can't write this thing as x times a function just in terms of t. So this will be a nonlinear differential equation. Okay, let me just pause the meeting for just 1 second and see if I can cut down on the noise a little bit by shutting some of the windows here. All right, sorry about that. Okay, let me just pause for a second and see if anybody has any questions about what we've been talking about so far. And I'll page through the pictures of everybody so I can see. Okay, no questions? Okay, so finally, there's this distinction of autonomous. I think we're going to hold off on that for now because it's not going to be relevant for a little while. Okay, So that's just a little bit about how we classify differential equations. Now, I probably should have talked about this first. This should have been how I kind of introduced the subject. Differential equations are extremely important in the sciences. They're of fundamental importance in physics. Literally everything in physics is stated in terms of differential equations. They're very important in chemistry. They're very important in biology in terms of modeling the rates of reactions, in modeling population dynamics. They're very important in finance. Basically, all of the sciences, differential equations are extremely important. And that's because we use them to take our ideas about how, for example, a physical system works and turn it into a mathematical model. So we turn it into something that we can reason about mathematically, and we hope that that gives us some predictions about what the way that the system operates and evolves, and allows us to understand the system better. So when we talk about this, I talk about this down here. So how these are used in practice. So the idea is that the way differential equations are used is that we start off with this real world problem that we're trying to solve. And one of the best examples of this is something like this, like population dynamics. So we want to understand something like how the population of bacteria in a petri dish grows, or something like that. So we make a kind of simplifying assumption, and we say that the speed at which the population grows should be proportional to the population. The more bacteria there are, the more opportunities there are for them to reproduce, and so the more the population increases, and the more population increases, the more bacteria there are, and it sort of feeds on itself like this. So we make the assumption that there's nothing that stops that process, and that there's just this proportion, there's this direct proportionality between the number of bacteria that exist and how quickly they are reproducing. So this is the kind of abstraction that we make. That's the abstraction step. So making that abstraction, we can take that idea and turn it into something that's purely mathematical. And so that's an example of that, is this equation right here. This capital P represents the population. I'm sure you're familiar with this example because we talk about it at the very end of Calc 3. But this capital P represents the population. And then this derivative of P with respect to T represents how quickly that's changing over time. And the assumption that we made that these things are directly proportional to each other is perfectly represented by this equation right here. So these things are equal to each other up to some multiple. So some multiple, we take some number and we multiply it by the population, the number of bacteria, and that gives us how quickly the population is increasing. Okay. So once we have a mathematical model, once we have our differential equation or system of differential equations, then we use the tools that we're going to talk about in this course in order to solve the equation. Now, the reason I do this in air quotes is because differential equations are notoriously difficult to solve, to get an exact solution for a differential equation. This equation right here that represents population growth is really the simplest example that we can possibly come up with in the area of differential equations. Well, we could possibly go a little bit simpler, but this is maybe the simplest interesting example of a differential equation. That's the reason that we talk about it at the end of Calc 3 as an introduction to differential equations, is because this is really the easiest thing that we can deal with, and we can come up with a solution in this case. But for the vast majority of differential equations that we're interested in, that come up in the real world, it's either very, very difficult to come up with a solution, or we just simply can't come up with a solution. We don't know how to do it. We don't know if something that can be written in a simple form even exists. So oftentimes what we do is, instead of solving differential equations, we approximate a solution to them. And so that's going to be an important topic in this class, is approximating a solution. Another thing that we do with differential equations is, looking at them, just try to figure out not an exact solution and not an approximate solution, but just get a feel for how things evolve over time. So is it the case that no matter how the system starts out, it always evolves towards a certain state? Is it the case that there are multiple states that it can evolve towards, and it always gets stuck in one of these states? Are there states that it always is guaranteed to move away from? These are all kinds of questions about the dynamics that are described by a differential equation, that we can possibly understand without getting a solution to the equation. So this is really the meat of the class right here, is the solve part of this triangle. Okay, so in the idealized situation, we got a solution, a mathematical solution. In reality, we have an approximate solution, or we have some qualitative understanding of the problem. And then we take that qualitative understanding that is still purely in the language of mathematics, and then we reinterpret that in terms of things in the real world. So the real stuff, the physical system, or the financial model, or the population model, or whatever. Okay. So that's how differential equations sort of slot into the rest of what we do in life. Okay. Maybe I'll back up a little bit and talk about the solving part. We'll begin to talk about that. So they give us an example here of a differential equation. We'll note that this is a linear differential equation. So we have this dx dt term. We can take everything that's multiplied by dx dt and collect it together as a function in terms of t. In that case, this function is just the constant 1. We can do the same thing with everything that's multiplied by x here. And finally, this is just a function completely in terms of t. So this is a linear ordinary differential equation. It's also a first order differential equation, because we only have the first derivative. That's the highest derivative that we have. Okay. And we can tell which are the dependent and independent variables because of the way the derivatives are written. So this is a derivative of x with respect to t, which implies that x has to be a function of t. Now, we start off with a nice situation to be in, which is that the book is just going to give us the solution to this differential equation. This is a pretty easy equation. It's a first order equation, and it's a linear equation, which makes it just about as easy as it possibly gets. And they just give us the solution right here. So they say that x is just simply equal to cosine of t plus sine of t. So if we have a solution, it's kind of the opposite of the situation that we were talking about with solving, getting the solution to a differential equation. Taking a differential equation going to the solution is a very hard process. Going the other direction and saying, we have a solution, we have a function, is this a solution to the differential equation, is a very easy process, because all we have to do is take derivatives. So we take the derivative of x with respect to t, we get cosine goes to minus sine, sine goes to cosine. So we see that here, the derivative of x with respect to t. So plus x, that gives us this right here. And what we end up with when we add these things together, the sines cancel out, we get 2 cosines. And so we have this 2 cosine t right here. I think we lost somebody. Okay. I have to occasionally page through here. I think there's a way to fix this so that I can see everybody at once, but I don't know how to do that yet. Okay, so we've plugged this into the differential equation, and we see that this is in fact a solution to the differential equation. The equation is true if we set x equal to this right here. And they take a moment to celebrate, and then they say, well, but wait, there's more. So they propose another possible solution to this differential equation. And so we take this other proposed solution and we plug it into the differential equation. And well, when we compute the derivative, we see that we get the same part for the cosine and sine, but we also know how to take the derivative of e to the minus t. So that's negative e to the minus t. And when we plug that in, all the stuff cancels out just like before, but now we have a minus e to the minus t and a plus e to the minus t, and those cancel out as well. And so we get the same right-hand side. And so we get another solution. So this illustrates an important point with differential equations, and that is for any given differential equation, it's entirely possible that it may have more than one solution. In fact, we may have infinitely many solutions. And so they make that point here, and they just tell us the fact that all of the solutions for this particular differential equation can be written in the form cosine of t plus sine of t plus, excuse me, some constant times e to the minus t. And we can kind of see why that's true, because we can do the same sort of derivative here. Instead of minus e to the minus t, we get minus c e to the minus t, and we get the c e to the minus t here, and the same cancellation happens. So this is definitely, everything of this form is definitely a solution to the equation. Now they tell us all solutions can be written in this form, but they don't tell us why that's true. So at this point, we're just taking their word for it. And they show here graphing these solutions, what we get. Now, an interesting thing about these various solutions is that it looks like they start off with very different values. And as time progresses, we're thinking of this, the x-axis, or the horizontal axis, I should say here, as representing time, because our independent variable, we're using t. So we think of that intuitively as representing time. So going in this direction, we're going into the future, and we see that all of these solutions kind of settle down to the same thing. So this is an interesting phenomenon, and we'll see this kind of thing comes up often in solutions to differential equations. And they have this nice statement here: solving differential equations can be quite hard. It's an understatement. It's a huge understatement. Like I said, for most interesting differential equations, we don't even know how to get a solution at all. We can only do approximate solutions. Okay. So we'll look at this example. This is the population dynamics example. And like the author says, we're just going to claim that we have a solution. So that solution is something written in this form: c times e to the kt. So c is some constant that we choose, and k is this same k, the proportionality constant here. So the first thing we can do when we're given a proposed solution is plug it into the differential equation and see if it works. And lo and behold, it does. So we take the derivative, the k comes down in front. We just kind of factor it out to the beginning here, and we get k times c e to the kt, and that's just the same as kp. Okay, now what? Right, so we don't know what the value of c is, and we don't know what the value of k is in this solution. If we're told a little bit more information, if we're told what the value of the population is at time 0, so at the initial, this is the initial population, and what the population is after 10 units of time have elapsed, so 10 seconds or 10 minutes or whatever unit of time, 10 years. If we're given the population at these two different times, then we can look at the solution that we get. We plug in 0 for our time, we get e to the 0, so that's just 1, and we get c. So when we plug this in, we get that c is equal to 100, right? So that's given us the value of c. If we plug in 10 here, then we've already got c, so we plug that in, and then we plug this into the equation, and we do a little bit of algebra to rearrange things, and we get that k is equal to natural log of 2/10. So it's approximately equal to this right here. So this illustrates another situation that we'll come up with a lot in differential equations, and that is that although a particular differential equation might have infinitely many possible solutions, usually those solutions are parameterized by some constant or something. So in this case, it was a constant, the c, so that parameterizes the solutions. And if we're given a little bit of information about the solution, for example, what is its value at the initial time, then we can figure out what that constant is. And so we call these initial value problems. So if we have a differential equation and we're told what its initial condition is, so we want to find a solution, and that extra bit of information allows us to pin down a single solution. So by the end of this summer semester, you'll have seen this situation a billion times, but this is what we're working on. Okay, they call these things the 4 fundamental equations. We'll just take a look at them very quickly. This one is, well, let's see, we have 11 minutes left. This first one is the population growth equation that we've seen before. So that's this is sort of like our archetypical example of a differential equation, because it's we know, or at least very soon we will be able to show that we know exactly what the solutions of this are, and we're able to, if we're given an initial condition, we're able to solve it completely. Okay, they just tell us that the general solution is this, but we'll see why that's true soon. Okay, the next one we have is this this one right here. We have the second derivative of y with respect to x, and this is equal to some constant times y. Now, in this case, they didn't write the constant just as k, or in this case, they're writing it as negative k. Here they're writing it as negative k squared. And the reason for this is not anything special about what the value of k has to be. We can take any value and put it in here as negative k squared, right? The reason they're writing it like this is because of the way that we go about finding this solution. So if we write our constant that's multiplied by y in the form negative k squared, we find that it's particularly helpful when we work through the math. We'll end up at the end with a k here in the solution. So again, they give us the general solution. In this case, it's parameterized by two parameters. So there's a constant C1 and a constant C2, and then we have something that's given in terms of cosine and something that's given in terms of sine. And then the period of these sinusoidal functions is given by k. So if we didn't write this as minus k squared, then once we got to the end of this, we would have to write this as square root of negative k or something like that. So that's why they write this constant like this. So you'll see this over and over. Okay, so the flip side of this is what happens if the constant here, we're implicitly saying that this is a negative number, right? Because, well, I should take a moment to talk about this. When you get into the field of differential equations, so far we've gone through calculus, or you've gone through calculus very likely, without ever having to deal with complex numbers or imaginary numbers. So these are things that arise when we allow for the possibility of taking the square root of a negative number, right? And if we assume that we're talking about negative numbers here and we're taking, well, this is the square of something. So when we get down to k here, we've had to take a square root. We need to distinguish between when it's negative and when it's positive if we aren't talking about complex numbers. So we're looking at this from the point of view of real numbers. When we deal with real numbers and we square it, we always end up with a positive number. So if we're talking about this k as just being a real number, we need to distinguish between the two cases. When this k squared is a negative number and when this k squared is a positive number. So that's the distinction between these two cases. If we allowed ourselves to talk about complex numbers, then we could sort of collapse these down into a single case. But we'll cross that bridge when we need to. Anyway, if we end up in this situation, we have a general solution which is written like this. Okay. Alternatively, we could write it in terms of hyperbolic cosine and hyperbolic sine. There's a decent chance that you haven't had to deal with these problems or these these functions yet in your mathematical career. It's just a couple of extra functions to think about. We define hyperbolic cosine like this. So it's the average of e to the x and e to the minus x. And the hyperbolic sine is half of their difference. These functions arise in a similar way to sine and cosine. If you remember the unit circle, and you take an angle, and then you go down to the x-axis, that gives you the cosine, and you go to the y-axis, that gives you the sine. You remember these things from the unit circle. So cosine, or hyperbolic cosine and hyperbolic sine are defined in the same way. And I'm gonna, if we have to deal with these very often, I'm gonna pronounce these cosh and cinch. That's sort of like the shorthand way that people have agreed upon referring to these things. Just because it takes a long time to say hyperbolic. Anyway, these things arise in a similar situation if instead of dealing with a unit circle, we deal with a unit hyperbola, then what we end up with is these definitions working in the same way as cosine and sine. And they give us what their derivatives are here. You could actually figure this out just by taking this expression right here is something that you know how to take the derivative of, right? We know how to take the derivative of e to the x and e to the minus x. So this is a straightforward derivative to do, but they tell us that. Okay. Now, maybe this is a good place because we got about 5 minutes left, so this will take about 5 minutes to talk about, so we can squeeze this in at the end. They give this as an exercise. Oh, and I should say, the web work is homework. It's there for you to practice dealing with all of the different kinds of situations that we'll deal with in this class. you'll probably find that you get finished with the web work pretty quickly. I highly encourage you, I very, very strongly encourage you to work these exercises out, these exercises in the book, work them as practice. And you can bring your solutions to these to me, and I will give you feedback on these. So it won't be for a grade, it's entirely optional, but it's very strongly encouraged because it will help you out a lot in getting an understanding of the material that you're dealing with. I can't emphasize that enough. The more that you practice these things, the better you will understand them. And the goal of this class is to understand these things. Okay, so this exercise, they say, check that both forms of y given are really solutions to the equation. And that's a pretty easy thing to do. We can take these things, we can take their derivatives. They actually tell us what their derivatives are, so we don't have to figure that out. Or we could deal with it from the point of view of e to the kx and e to the minus kx. And take their derivatives, plug them into the equation. And we can see right away that these things are solutions. Now, the more interesting thing, I think, is to look at this point where they say that the general solution of this equation is this, which is in terms of exponentials, or this, which is in terms of cosh and sinh. Is it clear to you that these are actually the same thing? Is it clear just looking at this that these are equivalent ways of writing the same thing? In other words, if we take this as our general solution, is this thing right here really just the same thing written in a different way? How would we be able to determine that? Well, what we can do is we can take this equation right here and this equation right here. Well, let's take this one because maybe it's a little intimidating to think of cosh and sinh and manipulating those things. Let's just replace those with e to the x plus e to the minus x over 2. So we'll just plug that in right there. And e to the x minus e to the minus x over 2, we plug that in right here, right? So when we do that, we'll have something in terms of e to the kx, right? Because for this cosh x, we've got a kx as being the input. So this x right here will be replaced with kx. This minus x here will be replaced by minus kx. So when we do that replacement, we'll have something completely in terms of e to the x, e to the kx, excuse me, and e to the minus kx. When we multiply that out, or when we add that, when we distribute this d1 and d2 and the 1/2, and we collect like terms. So we get everything, we collect everything together that's multiplied by e to the kx, and we multiply together everything we collect together everything that's multiplied by e to the minus kx. Then we get an expression in terms of d1 and d2. We'll get what, something like d1 over 2 plus d2 over 2 will be the thing that's multiplied by e to the kx, and so we can set that equal to c1. And then we get d1 over 2 minus d2 over 2 is equal to c2, right? Well, now what we've ended up with is simply a system of linear equations. And this is something that you're probably very familiar with because you've seen this multiple times throughout your math career at this point. So that's a system of differential equations. And we should know that how to solve that, so we can solve that and get C1 and C2 in terms of D1 and D2, and D1 and D2 in terms of C1 and C2. So that tells us that these are equivalent ways of writing the same thing. Okay, so it looks like it's 11:20 according to my clock. I'm going to stick around for just a minute in case anybody has any questions, but otherwise I guess we're done for today. And I'll see you tomorrow.